do something a little bit different for opening practice. Something a little more traditional. Maybe the stuff we've been doing, essentially, it's in this class of exercises called Vipassana, of practices. And it's all about just really noticing sensation and what's going on. But let's do something a little more traditional. So this is a box breath. And it'll make sense in a second. So the basic idea is just, so inhale for a count of 4, hold for a count of 4, exhale for a count of 4, hold that breath, don't take any breath in for four counts, repeat. So we got a nice square of breath. And does that make sense? Yeah. Let's just give that a shot. I thought that might be an interesting way to start the day. So just breathing, settling in first, and closing your eyes probably. And count breathing in. 2, 3, 4. Hold. 2, 3, 4. Exhale. 2, 3, 4. Hold. 2, 4. Inhale. Do that at your own rhythm, whatever feels comfortable for your lungs. Just finish up whatever round you're on. Just come back. Do some real analysis. Any questions? I would imagine so. I would hope so, but maybe not. Maybe you guys are just smoking this material so awesomely that there are no questions. And I'm not saying that facetiously. It could be taken that way. Any of those homeworks, I think it's due Wednesday. I think we had changed that. I officially changed that in world class. We feel good about that. And we'll be dropping a new homework 3 eventually. I kind of want to edit. I'm thinking about tweaking it a little bit. Yes, sir.
Completely different, but just it's not on the homework. But when I look up stuff for this class sometimes. It mentions the cut a lot. They said that's the other way you can start the course, kind of.
Oh, a Dedekind cut?
Yeah.
Yes.
If we have time, can we go over that?
Yeah, we totally can. I'd have to refresh my mind on all the exact details, but it's a way of I mean, we're eventually gonna get to, so what Michael's asking about is, how do we formalize the move from the rationals to the entire reals? In other words, how do we fill in, so the rationals are this crazy set of points. That doesn't do it justice at all. That's pretty bad, actually. There's a lot of big holes there. But it's this dust how do you rigorously fill in the holes to get all the irrationals to make the entire real number line? And there's multiple approaches to this. The one that Michael is asking about, and I think cuts, where we basically associate each number that's real as a pair of intervals. So for example, yeah, God, I don't even know how to think of this. Yeah, I would want to impress before I even start babbling about it. I know it has to do with basically pairs of intervals like that are disjoint, and then this interval represents a number, and it would be the number that's right at that cut point. So that's one way. The other way is with Cauchy sequences, and this would have been the way we're gonna head. And these are sequences that have a special property. Like, we'll just have to wait till we get there, and we'll be there really soon. So I kind of want to hold on to that, but this is all called constructing the reals. So yeah, cool, Michael. I will honor your request, but it'll take a little time.
It goes over it on 1-3-10.
Yes. Yeah, definitely. This is covered in our book, for sure. Anything else? That's like a super meta request. Yes, sir.
What it never mentions what because I did one of them and I hope, like 1.3.2, if it doesn't say that it's like rational or irrational, we always assume it's real if it doesn't say what kind of set it is?
That is correct,
Okay.
yes.
Okay.
Yep. Yeah, and 132 is the wide open real line.
Mm-hmm.
Except for like in C, like you said, C specifically restricts our attention to Q. Okay, all right, I'm gonna take your word on it that you're good. I will have your homework ones. I apologize, the solution set is up, you might have seen that. I will have those totally back to you on Wednesday at the start of class. Okay, so we are gonna actually talk about infinity today. For reading recommendations, you might wanna read through, I should have recommended this ahead, 1.5 and 1.6. After today, they're gonna be easy reads, I hope. And you could go ahead and kind of get a start on section 2 if you want. 2.1 is just like the intro, at least read 2.1. But if you want, you could read up through 2.2. I think we'll be there on Wednesday, for sure. And then we'll start talking about Cauchy sequences eventually, probably next week. All right, so let's see where we're at together. So I've got a function f that maps from some subset of the reals into another subset. Does that notation make okay sense? Yeah. So this is the domain of f. It's a subset of the reals. This is the codomain v. It may or may not be the range. So what are you? I want to check. This is like a little karma-free quiz. What are the definitions of each of these things? Can you come up with those? And it's like good to try to pull them from the recesses of your brain and see if you can write a formal definition, not even just an intuitive one. That's good. What is a formal mathematician's definition? And then let's hold off. I want to give everybody a chance, but I'll come to you first. And I might even come to you for 2 versions of one of them. Oh, we'll probably spread the love around a little bit. Michael, you were definitely excited about giving me one of these.
I always
Which one?
like surjective.
Okay, cool, then you will be surjective. I did mean that pun-wise too, kind of. Surjective.
If for all B in B, yeah, for all little b in B, there exists an A such that f of A is equal to B.
Cool, and I love that, and let's just get that in there.
Yeah.
But that was, I knew you meant that. I can hit everything in the set B with the appropriate input in A. So that's a good formal definition of surjectivity. Can somebody else give me an injective? Ashley, you got an injective definition? Diana? Got one, no. Trinity? Was that tiny? No? That's okay. You've been sick. You got a lot of guys.
I don't remember, sorry.
Oh, it's okay, I'm sorry. Is it hard to talk?
Sometimes still. I said, I don't remember injective really well, but I think it's the distinct elements mapped to other distinct elements.
That's a beautiful one. That's a great one. So let's go with yours first. So this is version 1, V1. For all and let's do X and Y's, right? Because otherwise it could get a little weird. X and Y in A, where they are distinct. And that's what Anna means by that. They're not the same thing. It follows that their outputs have to be distinct. I love that. That's great, Anna. Thank you. Noah, do you have a different version of that for me?
The counterpositive is that if FA equals FB, A equals B.
Love it. Cool. So the contrapositive, right? So both are really useful in different circumstances. Contrapositive is usually great if you're trying to demonstrate injectivity of a specific thing that you're given. So this version is not this implies not this. So in other words, for all X and Y in A, f of A equals f of, shit, put X's and Y's in there. What a chump. I'm the chump. I wrote it. If the outputs are the same, then the inputs are the same. Great, 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 great. This is a great surjective. We usually only go with this one here. There's not even an implication, so maybe we could write it that way, but there's not really any versions of this. And then how about, what is surjective? Excuse me, bijective.
I was like, wait, you're just.
Sorry, yeah, what is bijective? This one's the easiest. Trinity, you say it's easy, you tell me.
It's bijective if it's the injective answer.
Thank you. Yeah. If F is 1-to-1 and onto. So I'll kind of get a little slang in there. This is 1-to-1 and this is onto. And once you're a mathematician, you can never hear the word onto normally, right? Like it comes up anywhere else and you instantly think surjective. Because our minds get warped in the best way by math. So what about this? Let's another definition. We have two sets, A and B, and we say that A is equivalent to B, i.e. A has the same cardinality as B if, can somebody help me here? One or two sets the same size. But this is a much more general notion of size, so you can think of this as same size. Yes, Michael.
If there exists a bijective function that maps A to B.
Love it. So if there exists, I'm going to show you some slick math notation. So there's some function, f from A to B, that is a bijection, 1 to 1 and on to. That's it. That's fun, right? So part of the fun of being a mathematician is writing weird stuff in a strange language. And there we go, we've got new stuff. So, let's talk about some cardinalities. And we got a definition. Let's get some, more definition. And then we'll start having some fun. A set A, I guess we'll call it an R, is countable if what? Finish the definition. Everybody try to finish the definition. What do you think it is, even if you're not going to necessarily say it out loud? Good way to practice. Diana, what's countable? You know? Got a sense? Anybody want to help here? Ashley, what's countable? Say that again? Finite is definitely a kind of countable. So, let me be more precise. Countably infinite. Let me be a little bit more precise about where I'm headed. You're totally right that a finite set is countable. Countably infinite. If what? There exists something.
The bijective function from the naturals to
Yes.
A.
If there exists a bijection f from A to the natural, let's do it the other way. From the naturals, it's usually better to have that as your input to A, which is 1 to 1 and on to. What does this mean in practice? That I can make a list, i.e., we can list all the elements. Now, this is a mathematician's list, where it could be infinite and will be infinite. But what we're saying is we can establish a pattern that anyone can follow and locate a particular item in the list. So you've got your naturals here, and then you've got your elements of A over here, and all you're saying is that you can make a correspondence like this, and this in its entirety gets all of A. So this hits. That's all we're saying. So I can make a list, aka a sequence, of things in A. A equals that beast right there. That's countable. If that list terminates, then we have a finite set, and that is certainly a countable thing too. But we usually distinguish, and let's actually make that distinction formal, that a finite set has a 1-to-1 correspondence with a subset, with a finite subset of the naturals. So we would say A is finite if there exists an F from the set 1 up to K to A, that is 1 to bless you, 1 to 1 and on to, for some fixed K. There's a nice definition of finite set. Bless you. Gosh, all sorts of stuff's going on all over the place. I appreciate you showing up though anyway.
Yeah, I was worse than
No, it's good. I know it's not easy. Okay, cool. So, what are some countable sets? somebody give me an interesting example of a set, not and. Michael. That's good, that's good. Low-hanging fruit, but still an interesting idea. So, example, the even naturals, i.e. 2, 4, 6. Michael, can you give me a bijection, please?
F such that f of n is equal to 2n.
Beautiful. Let's get really formal with this. This is a good place to show that, you know, how we approach demonstrating bijectivity. Then we claim that f from the naturals to this set, well, let's call it A, is 1 to 1 and on to. So first thing is, I need to show it's 1 to 1. Might seem obvious, but we do a lot of things that seem obvious in math, right? So you see f is 1 to 1. We're going to use that contrapositive definition of injectivity. So assume that f of m equals f of n, and I hope to show that the only conclusion is m equals n. That's the only conclusion. Well, this means, go to the definition of f, that 2m equals 2n. It's starting to seem a little basic, but that's okay. I can cancel 2 with no problem. I.e. m equals n. Check, it's 1 to 1, super cake. To see f is onto, take some element, let's call it a in A, not to be terribly uncreative. We know that everything in A has the form 2 times something. I'm really into K this morning. We're just saying the obvious things in a detailed way. One of the pains of being a mathematician is this kind of precision. Thus this. So f of k equals 2k equals a. And we know the input now. It's basically half of a, right? I.e., let's just do this. F of a over 2 equals a, and that's a natural. Bye, Anna. See you on Wednesday. Probably.
Hopefully.
Yeah. I feel like even if we have a snow day and they cancel classes, I might like be online anyway, just to meet with you guys. I'll cancel all my other classes, but like, we'll hang out. Because this really is the majority of it. So, does this make sense? Do we see how to, see how to proceed with this? All right, let's get to some more interesting results. Claim. Oh, actually, real quick before we go there, because this might help. What about Z? Is Z countable? And somebody help me. So, Noah, you're nodding. Can you help me come up with a scheme?
If n is odd, then n minus 1 over -2.
Over -2? We
or
could,
just
probably.
negative. Just put a negative.
I like it.
Yeah.
That's
somewhere.
different. You're shaking shit up, man.
And then if n is even, n over 2.
Okay, so what is n?
A natural number.
Okay, cool. So we're going to create this f. And I got this ass backwards here. This is the output, right? Usually we kind of say it the other way, but that's okay. We're family and friends here, so math family. So this F maps from the naturals into Z. And let's actually, I always like to make a list to understand patterns. So let's make a list of what Noah is proposing here. See where it goes. So n equals 1 is odd, so that's going to give us 0. N is 2, that's going to give us 1. Now here comes the fun with the negative. I'm stoked about this. When n is 3, we've got -1. Yeah. Does that sound right? And then when n is 4, we've got 2. Oh, this is cool, Noah. Nice. I like this. I've seen something like this, but never this exact one. When n is 5, we get -2. Oh, so that's pretty. And then I'm going to take a crazy guess here. Is that right? I think it checks out. Then I'll just check. Let's see, 7. Yeah. Cool. Good stuff. So look at how Noah made this list. He basically kind of took Z and folded it on itself, lifted up the negative half, and interleaved it into the right half. This, by the way, you're going to hear this word a lot in this class. Interleaving. It's just a freaking great word. It sounds so smart. And it's just the basic idea of making a zipper of things. And we're going to be doing this like crazy. It's not a math word, it's just a great word for math. So interleave the negatives. Wow. Well, I know words, but I can't spell some basic ones. The negatives and the positives. Beautiful. And that's we could have just given it this way as well. Oh shit. Properly though. That also establishes it. What's cool is Noah's formula allows you to address the questions of 1 to 1 and on to you tell me what number you want. I think we can find it in that list. Good shit. So Z is countable. Let's take a look at something, and that almost seems reasonable. The only thing that might throw you off is the double infinity, right? It's not bounded on one side, but we can just fold it in half and we're good to go. So, what about our big result for today? And this is actually a pretty ridiculous result. It doesn't seem right. And there's a number of ways to prove it. Let's take a look at kind of a nice straightforward way. So this is courtesy of Cantor. Cantor is to thank for a lot of the stuff we do in this class. One of the founding people for real analysis and calculus and math and just making everything on solid footing. So Cantor's proof, he was really into diagonals, as we're going to see today. He was super into diagonals.
I think all of those people besides Reddit were,
I thought that was like an official announcement. It's just someone being really loud. Let's close the door. I wouldn't close their door too. I don't know if that's rude or not, but. What's that?
That would be seen as a bit rude.
So we're speaking out loud with them.
That was pretty rude. So, okay. Cool. So, oh well. I live to just enrage people. It's part of my lifestyle. All right. So Cantor's idea was, can we do something kind of like this interleaving, but on a multi-dimensional scale? So let's just, first off, here's the easy one. Let's just look at the positive rationals to start with. So that little plus just means only the positives. So this is set of A over B. A and B are naturals and both positive. This one's easy, and this is one you should keep in your mind just to like pull out and impress people whenever you need to have a magical trick. So here's how this works. We're going to come up with a list, and the first list is going to be all the fractions with 1 on top. And you could think of that as commas or what have you. And that keeps on cruising. And then let's make another list with all 2's on top. All 3's on top. And you get the rhythm after this. You probably had the rhythm before this. Okay. And, you know, forevermore, keep this going. So Cantor's great insight was, here's one way you can't make the list that a lot of people want to do. This is a natural thing. I'll just take this first list and tack this one on the back, and then tack this at the end, right? So just take this and glue it down there. Take this and glue it down there, almost like you're putting strips of paper together. That is not going to work because we can't reach the end of it. There is no end, and it's not a clearly defined pattern. Like, how would you get, if we just tacked this onto the end of that, how would you explain to someone to get to 2? Keep on going. That's not a good explanation. So what Cantor realized was that, oh my gosh, we could actually do a pattern like this. And I want you to notice the commonalities on the diagonal. Notice how on each diagonal, the sum of the numerator and denominator is constant. So these add to 3, these add to 4, these add to 5. And so what we're doing is grouping things by the sum of A plus B is a constant. And then just tacking those strips together. So we're making these diagonal strips and then gluing those together. But this is a nice defined pattern. And you could theoretically let someone know how to get to 3/5 or 17/450. Eventually it's clear you will hit all the numbers in this list. What is a problem here? Michael?
The elements appear many times under different forms.
Yeah, no, this isn't unique, right? So for example, this diagonal is all 1s. So in some ways, I'm repeating a lot of things. I'm listing a bunch of stuff, but I'm repeating things. So we have more here than we do rationals in some way. We know that the rationals are finite, are infinite, an infinite number. We've shown that there's an upper bound of a countable infinity, but there's definitely more stuff here than there are rationals with all the repeats. So the problem is not unique, non-unique representations. And that's actually going to be kind of a theme for a couple of things we talk about today. It's not necessarily unique representations. So our book actually has a different approach that eliminates this problem. Let's take a look at that approach. So, to avoid this problem, we need a different approach. And in fact, with this different approach, we're just going to get Q as well. I could have done all the Q's and included negatives as well in here, but it gets a little messy. So let's show Q itself is countable. So I just wanted you to be aware of that diagonal argument. It's really famous. And it's a good thing to know as a mathematician. This is a little more arcane. So here we're going to create a bunch of subsets. First one is we're going to have A0 is just 0. And we're going to break the rationals into actually a countable collection of sets and then list those sets out. So A sub 1 is going to be let me make sure I'm getting their sets right. Yep, okay. Actually, they're calling this A sub 1 and then this A sub 2. Let's do that. And I'll show you why that was a problem for me in just a minute. So this guy and this guy. After this first set, this index will represent the sum of the absolute values of the numerator and denominator. So notice there's just 1 and 1, so 2. So A sub 3 is going to be all the things that could add to 3. And then we take the plus and minuses of all that. So in other words, 1/2, 2 firsts, and then their negatives. And so just could you just like, so that we're all thinking and not just writing, what's a 4 going to look like? Make sure we're on the same page. I do have a reminder that I do have office hours tomorrow if you still need to talk about your homework. Hoping everybody's kind of far in it, and feeling good about it.
But then you have the same problem. Because 2 over 2 is the same as 1 over 1.
Oh, you're right, you're right. Let's not do that then. Yep, that's good. We're not going to do that. So don't list things that have already been listed. That's it. There you go, Noah. Thanks for busting that. So let's see, I didn't do that here yet, did I? I don't think I've done that yet. So let's just, don't list non-unique fractions. So yeah, so we're not going to do 2 over 2, but we are going to do 3 over 1, and then we're going to do negative 1/3 and negative 3. And so maybe make a little note here is don't include plus or minus 2 over 2. And thank you, Noah. Yeah, because now in this way, each of these sets will be completely disjoint with this scheme, but only with that added in. So each A sub k is finite. That's essential because now I can actually stack them in a row. If they were infinite, I couldn't do that. So each A sub k is finite and distinct. Thus, the list A sub 0, or A sub 1, A sub 2, A sub 3, the sequence of sets contains every single rational number. You tell me what rational you want. So where is P over Q? What set would P over Q be in? And you could work that P and Q are positive if you want.
A sub P plus Q?
Yeah, beautiful. And let's take care of, just in case things are negative. Slap some absolute values on it. It'll be in that set somewhere. Which one in that set, we don't know, but we know for damn good and sure that it is in there. So that means every rational occurs in this list, and only once. And so that's another way to show that the rationals are countable. This is a much more precise and solid way to do it. I like the other because it's just intuitively lovely. Any questions on this stuff, friends? Because we're gonna move.
Is there a smaller infinity than the countable infinity? Because I feel like you said that it was infinite and had an upper bound of the countable infinity, so does it make it the countable infinity?
So that's a great question. So we've got finite, and then we've got countable, and it is going to turn out for us that this is the smallest infinity. There is a conjecture. Did I mention the continuum hypothesis in here? I feel like I might have, but maybe not. Yeah, so the continuum hypothesis is that there is there. Says that there might be an infinity between a countable infinity and a finite. So there's a smaller infinity, Noah, but no one has found it. And we don't know that it can't exist. So the only thing we know is that if there's an infinity between here and here, then everything's okay. And if there isn't, everything is okay. So it's one of those things where it's like, we don't know. It's kind of cool that we don't know it. We don't. So this is like, I don't know if I'd go like spend a lot of time thinking about this, but you never know. I shouldn't stop you. I think you'll just go crazy, is what I think. We don't know if there is a non-finite set, let me say this officially, with cardinality less than, and here's the symbol that for countable infinity. So this is Aleph null. It's a Hebrew, first letter of the Hebrew alphabet. What's that?
I was saying we steal everybody's like alphabet.
Oh, absolutely. We ran out. We ran out, and we needed more cool symbols. So this is Aleph null, and it represents the cardinality of countability. But we don't know if there's one underneath that, and it doesn't, you don't go dividing cardinalities and stuff like that. Yes, Michael, sir?
This is just a question about notation. Do you care what notation we use as long as we're clear?
In terms of what?
Well, like in cardinality, I got used to in abstract algebra, right? The two lines around the set.
Oh yeah, that's great. So I love that. That's a great notation. So I spent one time, I still can't even make this symbol consistently. I spent like a day practicing it, and I still can't make it nice.
Yeah.
So that's totally cool. I think our book uses this, but that either one is quite fine. So cardinality of n.
And then I use the negation, like the complement symbol from logic and proof, the little, yeah.
For what?
Like not in a set? Is that
Oh yeah, that's
correct?
good.
Okay.
Yeah, yeah,
Okay.
definitely. I mean, you can also,
Cardinalities.
that's also pretty cool, easy not element of.
Yeah.
As long as I can understand what you're saying, as long as you establish your notation, if you want to like create new notation and give me a key, that's cool. I'm into that. Okay, so the rationals are countable. Aleph null is our smallest infinity, our smallest cardinality. Now, like I was hinting at this, we don't use these numbers like regular numbers. So you're not going to talk about adding cardinalities. that doesn't really make any sense for the most part. Except that if it did, the answer would be that. And now it's just garbage because it looks like L of null is equal to 0. And but putting together things of the same cardinality don't necessarily boost you up. For example, we know that this set has cardinality L of null. We also know this set, or we can easily surmise, oh shit, what actually not is this? This set also has cardinality L of null, but the union of these two sets doesn't get any bigger. So when you union those two together, you get this set, and that still has cardinality L of null. But we are going to talk about how to build bigger infinities. It's going to turn out that you take your current level of infinity, and we can keep building a stack of them up, bigger and bigger infinities. But we have to talk about a certain way to do that. So the next one up. The next one up is uncountable. So if a set is infinite and not countable, wow, that word is countable, sorry. It is uncountably infinite. That's not a very imaginative definition. But an uncountable set can't be listed. This is what you really need to know intuitively. And Noah, I actually said something quite wrong. I got my bearings off here. The continuum hypothesis is actually not between this and finite. This is definitely the lowest level of infinity, countable. What I should have said, and this is what I said before, is that here we have countable and uncountable. So let me correct what I said before. The continuum hypothesis is actually about an infinity between these two.
So then countably infinite is the smallest?
It is, sir, yes, definitely. Countably infinite is the smallest infinity. That's a pretty certain statement. So apologies for the confusion. Uncountable set can't be listed. Let's just get right into it. Claim. So the minute, all the rationals, take the rationals, all those, put them all together, Q, there's a listable, they're listable, no matter how crazy that thing looks. The minute we fill in the holes, that becomes uncountable, which is pretty wild. And we're gonna look at two proofs of this today. The first one, which we talk about in the book, uses the nested interval property. So proof one is use the nested interval property. And do you remember, see if you can write that down. What does the nested interval property say? Recall. nested, there's something in common to all of them. That's the nested interval problem. Taking these intervals, and you keep intersecting them, there will always be something inside there. It's like I1, I2, I3, down the row. So here, what we're gonna do, and all the proofs that R is uncountable that I know of, proceed by contradiction. So we try to make a list and then show no matter how you make that list, you can always produce something that isn't in the list. All your lists will fail. Proceed by contradiction. So we assume R is countable. And that means I can make a list. So then I make a list, because I want some things to grab onto, i.e. R is just some things listed out like this, x1, x2, on up the way. Let's see, how do I initialize this? Oh, yeah, okay. So we proceed kind of with a step-by-step algorithm. Let I sub 1 be a closed interval not containing x1. And let's draw a picture. So here's x1, somewhere on the real line. Here's I1. Pretty easy to pick an interval not containing a single point. It'd be hard to go wrong, even just randomly. Is everybody cool with that? Does that sound like reasonable? Yeah. So then, next step, let I sub 2 be a closed interval in I sub 1. So now I'm gonna nest. I'm gonna pick an I sub 2 inside here, but I wanna make sure that it doesn't contain x2. Convince yourself that that is something we can easily do. We're not going to go into the details for an algorithm, but can you do that? Put your x2 somewhere, just a couple of circumstances. So just convince yourself that is doable. And once you do this, you're good for the rest of the game, because it's all just little mirror images, tinier and tinier mirror images of this. Replicas, not mirrors. So check it out. If x2 is outside of I1, then it doesn't matter what I pick for I2. Here's I2. Great. If x2, I wish I had my little whiteboard now with my magic iPad. If x2 is inside here, I've still got lots of options. I could pick it, there's some positive space here. I could just pick I2 to the left. If x2 is one of these endpoints, that's okay too. I can still do something like this. But no matter how I roll with this, I can always do this. No matter what x2, I2, and I1, and x1 are. So repeat forever. Let I sub k plus 1, I'll say that, be a closed interval in I sub k not containing x sub k plus 1. So we've created a sequence of nested intervals. Let's summarize what we got up here. And this might actually help in the thought process of the contradiction. So we've got I1 contains I2, contains I3, contains I4, contains the chain. And let's also know what we know that x1 is not in here. So x1 is not an element in there. x2 is not an element in there. x3 is not an element in here. On down the chain. Okay, so what does the nested interval property say about the intersection of these intervals? What does that tell us? Yeah, what's that like? Yes.
The nested interval property says that that intersection is non-empty, but
Yeah, okay.
by what we're doing for any x sub k that we want, we will not see it because it won't be in I sub k plus 1.
Yes.
So by that other one, it's empty, right?
Yeah, so almost, let's not go that far.
Yeah.
Everything up there is super beautiful. So Michael's saying nested interval property says that this has actually got something in it. It has to have something in it. But that something can't be any of these things in this list, because none of the things in that list are in every set. As soon as you move to the next set, you've lost a bunch of stuff before that. So let me write this up a little more formally. Let x be an element of this intersection. So I'm going to pull something out of that intersection. X cannot equal x sub k for any k. Because x sub k itself is not in I sub k. So it can't be in the intersection. If you're not in one of these sets, you're not in all of those sets, for sure. And the way we built this crazy construction, guarantees that whatever is in common to all of these couldn't have possibly been in that list. What do you think x is then? Who knows? Just something weird, right? Just something quite weird. What if the x's were all rational numbers? What would that force this to be? So let's say I let x1 through whatever, that's all the rationals listed out. What have I just built? An irrational. This must be an irrational if those were all rational. So I build something outside of that original set. Here we don't know. It could be, there could be square root of 2 in there. We don't know. But we built something that is not contained in there at all. Thus, and the problem came when I tried to list this all out. R cannot be listed. Because if it could, all this garbage would happen. And this garbage says that it can't be listed. Cannot be listed and must be uncountable. Let's take a look at another proof, but we need to do a little bit of finagling first. So let's look at some other things that are also uncountable. So now we've got R is uncountable. And the symbol for that is a fancy C. So let's summarize what we've got here. So the cardinality of the reals, and we can use Michael's preferred notation, I'm cool with that. Makes sense, it's like absolute value, right? Like size, so it's very intuitive. Is this symbol C, and this stands for continuum, which is also another freaking awesome word, because 2 U's in a row, right? The minute there's 2 U's in a row.
I was wondering if you spelled that right, when you were like 2 U's in a row.
What's that?
It looks wrong.
It does, I know, now you're making me worry, because I'm not a great speller. But like vacuum, right? Is it, okay, all right, that's good, all right. And an honor student just approved me here, so I know I'm doing good. All right, so, and then we also have cardinality, let's just refresh this. Equal to aleph, null. Right? So now we have these things. What other things? We know a bunch of things now that have this cardinality. What about this? So let me give you a claim. This is going to help. The cardinality of the open interval 0 to 1 is C. So what do we have to do? So in other words, there, in this set from 0 to 1, not including 0 and 1, there's as many real numbers here as there are real numbers everywhere, which also sounds insane. Because I can see that there's more. There's literally, to the left and the right, there's freaking real numbers. But there's the same number here. So what we have to do is create a bijection from R to 0, 1 or vice versa. So to prove this, create F, and let's go, once you create a bijection, it doesn't matter. 0 to 1, that is 1 to 1. That's all I need. Can you help me? Here's R, here's 0 to 1. I need a function. I need to draw a picture in here that is 1 to 1 and on to, just in this little strip. Michael, what do you think?
I'm thinking of the arctan one, but I don't know how to scale it and how to add it. I can't
So
remember.
this warms my heart that you know what arctan looks like just off the top. I hope we all do in some way. So I think Michael, yeah, you're thinking something like this, yeah? So we could do arctan, let's do that. It's fancy. Arctan itself would normally do this. Let's see, pi over 2, negative pi over 2. Right, so that's arctan. So what we would first want to do is maybe scale it. Right, so scale it so that it's only a unit high. So let's see. So yeah, so we want to, so like if I multiply by 2 over pi, let's go slowly. So 2 over pi arctan of x would look like this. Right? Like that. And then I still want it to be a little, so let's actually cut it in half again. So let's do 1/2 of that. So that that's a half and that's negative a half. And then just shift it up. And then I can just lift this up. So I'll just add 1/2 to the outside. And that should look like this. And we'll just say that's the real axis there. So there's a function. 1 over pi arctan of x plus a half. That gets us there. Here's something a little less tricky. This is the one I came up with. Every time I talk about this, I try to come up with a new one. This one is actually important for neural networks. Does anybody do neural network stuff in here? No? Okay. This is useful for neural responses. But my function was this. Or so think about it. What is the limit as x goes to infinity? 1. What is the limit as x goes to negative infinity? This will go to 0, 0. And so you get 0 over 1. And when x equals 0, you're right at a half. So that function would also work. Then you would probably want to just prove to the skeptical reader that your function was 1 to 1 and on to. but we won't. But we could. I actually did it just for fun, because I just wanted to do it. I wanted to do the one-to-one proof and the onto proof, because I like logs and stuff. So there's a great thing. So now, check it out. Now we've got a new thing that's uncountable. So here's a great new representative of our uncountability, 0 to 1. And it's going to make this next proof actually work. Can I stop and just like take any questions? You just need a breath or anything. All right. Yep.
When they did in the book, they did it the reverse way, where they went from 0 to 1.
Yeah, definitely. And we could do that as well. The good news is once you have that bijection, you can flip the domain and the range and you're totally kosher. So they can, what did they actually do? Oh yeah.
They did some polynomial.
Ooh, they did a fun little polynomial, yeah. I see. Indeed. And I think they actually proved negative 1 to 1 was countable as well. Uncountable, excuse me. Lots of ways to get things done, definitely. So now you've got extra examples. Here's a new proof, the second proof, that the cardinality of R is C. So here's what we do know. We will show that the cardinality of 0 to 1 is C. And we know that there's a 1-to-1 correspondence between this set and R, which we've just demonstrated, since there exists a 1-to-1 onto correspondence twixt 0, 1, and R. We're accomplishing the same thing, and that should have a T. It just means between, saying it in a stupid way. So, again, hey Cantor, there's a diagonal coming up. Assume the set 0 to 1 is countable. And I can make a list of it. Now, this relies on decimal representations of numbers between 0 and 1. So any number inside here can be written using a decimal expansion.